Hello everyone and welcome to a new chapter in waves. In this chapter, chapter 2, we cover the superposition of waves, which is also known as the interference of waves. Now, let's get started. Okay, before we start, think about this. If you have ever been to a concert, in a concert hall, you notice that audience receives simultaneously different sounds. One's coming from the instruments and different instruments as well, and some others reflecting off the boundaries and the surfaces in the hall. That's why, in order to have the best experience, when we construct or when engineers construct a concert hall, they always take into consideration the phenomenon known as the superposition of sound waves. Another daily life application is the use of mufflers. In cars, we have mufflers that reduce the sound produced by the car. In order to cancel the sound produced by a car, in fact, we don't say cancel. In order to reduce that sound, we send some type of waves which are opposite to the waves produced by the sound of the car and try to cancel them out. This phenomenon or this technique of noise cancelling is also used in mufflers in headphones. Nowadays, if you buy some headphones or some earphones, you might find something called ANC, anti-noise cancelling. Okay, this is a special technique in which we use interference or superposition to cancel out any noise sound which is produced all around us. So what is interference and how is superposition applied and studied? Let's check that during this chapter. Before we start with the lesson, I always like to ask this simple question. What happens when two waves meet while they travel through the same medium? Will the waves pass by each other? Or will they collide just like pool or billiard balls do? What's going to happen? Before we check the answer, let's watch this simple video together. In this video, we have produced a wave, or in fact, two pulses, two signals on two sides of this object that you can see on the top. On the bottom, you can see the wave or the pulses as they propagate, one from the left, one from the right. Okay, notice as they meet, they produce a new wave, then each wave continues its path. This is interesting, right? Check it again. Okay, you notice we have something happening between these waves. So what happens when two waves overlap or reach each other? We used the term collide before. Now we know that the term collide isn't correct. Okay? In fact, the waves add up algebraically on the level of amplitudes. This phenomenon is called superposition of waves. This is the subject of our lesson. This is the core part of this chapter, right? Now, if you consider the figures of the waves that we have seen before, or the experiment that we have just watched previously, you notice that in the first figure, we had the two waves approaching each other. Over here, I have resembled the wave by red and blue. On the left-hand side, you can see a red pulse moving to the right side, while on the right-hand side, you can see a blue pulse moving towards the left side. It is important to mention that these two waves are of the same nature. They are both waves moving on a certain object, let's say a rope. Not only that, definitely they have the same speed because we are in the same medium. So the two signals traveling towards each other are gonna reach some point where where the roads will cross. We can say crossroads or whatever you want to call it. Okay? We are interested at what happens exactly at the point where they meet. In the second figure, I've chosen a very particular instant in which the two waves happen to be present at one particular point, or rather say in one particular interval. Notice from here to here to here and to here. Okay? So what happens if you notice point by point, if we take for example this level here, The wave in red and the wave in blue happen to have the same displacement. So you notice the resulting displacement is the sum of this and this again to have. While if you check the crest or the amplitude, since the two amplitudes are on top of each other, so at this level, the first amplitude, A1, and A2, the second amplitude, add up to produce A1 plus A2. Now, which is what is more weird, in fact, if we check what happens afterwards. Each pulse continues its path as if it has an internal memory remembering its initial amplitude. So after they overlapped, each wave kept its own amplitude and continued moving in its direction. Now, why does that happen? Why doesn't the waves just collapse? Why doesn't the waves simply split or divide equally? That is related to some term which is to be studied in higher level waves. We are not supposed to study that on this level of the course, but keep in mind that after superposing, the waves continue their path, keeping their original and initial characteristics. So, to define superposition, the principle of linear superposition of waves, let's say, states that when two or more waves or pulses of the same nature meet simultaneously at the same time at a point, the resultant elongation of that particular point is the algebraic sum of the elongations due to the individual waves. Each pulse gives its own displacement, its own elongation, its own energy, yes, to the point, so that this point behaves accordingly, or takes both energies and add them up according to their signs. Okay? In order to construct a resultant pulse, we add the displacements point by point. Okay? Let's check that in a simple example. We can see here at time equal to 0, two pulses are drawn. On the right hand side, you can see a pulse in the shape of a triangle, and on the left hand side, you can see another pulse having a trapezoidal shape. These pulses are moving at the same speed towards each other of 1 meter per second. If you look at the axis, it is also labeled as using a scale of 1 meter. So you notice, or you can easily tell that after 1 second, this wave, the one to the right side, becomes here, and the one to the left-hand side becomes here. Okay? After another second, let me change color. This wave progresses and becomes here, and this wave progresses and becomes here. Now, from this instant and on, notice that the waves reach the same position at x equal to 4. The wave to the left-hand side just reached there, and the wave coming from the right-hand side just arrived there. As of now, after 3 seconds, after 2 seconds in fact, the waves will start overlapping. At the time 2.1 second, we will have overlapping, 2.5, 3, etc. Now, I have chosen a very particular instant, which is after 3 seconds. So at time equal to 3 seconds, the two waves overlap. As you can see here, the wave coming from the right-hand side is drawn in red with a dotted figure, and the one coming from the left-hand side is drawn using black color. Also dotted because we do not know what's going to happen. Now, we said that the points add up point by point. So in order to find the resultant, suppose that this part here, which I'm going to color with in green, is the part of a rope or the medium that is affected by the two waves. So each point here, which I'm going to add on the figure as well, let's say this point, okay, I'll highlight them a bit more, this point, and let's go to this point so that I don't mess up the figure a lot. Now, at each point, I check both waves, and for that I will use, I'll choose blue. Okay, at this point, for example, the wave coming from, or the red wave, let's call them red and black. Okay, I think that's easier to distinguish. The red wave has 0 displacement and the black as well. Adding 0 and 0, which is A1 plus A2, gives 0. At this level, we are dealing with transverse waves. I draw a line perpendicular to the direction of propagation. You notice that both waves happen to have the same displacement, which is around half a centimeter. Great. So the rope is receiving, or the medium is receiving two energies, two pulses. The first is pushing it up half a centimeter according to the figure, and the second as well. Adding them together, I get a pulse which is here, or a displacement which is here, to use accurate words. At this point, okay, let me choose yellow for that, okay? Again, this point is receiving two energies, this from the red and from the black. 1 centimeter and another centimeter to give 2 centimeters displacement. Continuing with red, at this point 0 and 1, okay, so it becomes 0. So, joining all these points together gives me a clue about the resulting aspect or shape of the medium affected by these two waves. So this is what we call the resultant displacement or elongation. Okay? So the rope looks like that. Adding displacements point by point, this is what we're going to have. So if you look at the medium, you will notice that when the waves overlap, you will observe the figure that is drawn on the bottom right side. Okay? This might be a bit tricky. With some exercises, it becomes easier. However, what we need to focus on, as for now, is that when a certain medium is affected by waves, when these waves reach each other, we have a principle or a certain phenomenon called superposition. In superposition, we simply add both magnitudes of, or both displacements or elongations of the waves, and according to that, we find the resulting displacement. So, this is the principle of superposition. Right now, you might be asking yourselves too many questions, as for example, what's going to happen if one signal is moving or displacing up while the second signal is displacing from below? So what happens if the two signals or waves arriving at a point arrive in opposition as for their displacement, not in opposition as for their motion? These are two waves. We do not say opposition and in phase. In fact, when the two signals overlap, we distinguish between two special types of overlapping. What are these two types? Constructive superposition, or simply known as constructive interference. You will notice that in the upcoming videos and parts, we're going to use CI for this, as in constructive interference. When the signals have the same sense of elongation, I've chosen in the figure two elongations above the rope. The elongations can be from below as well, such as like this and like this. The resultant is also gonna be, okay, adding this one and this one as well. Okay, so yes, constructive interference happens when the two waves reach a point and these waves have the same sense of elongation. Destructive interference or destructive superposition is when they have opposite elongations. If you look at the figure on the lower right side, you notice that the pulse coming from the left and the pulse coming from the right have opposite signs of displacements. I was about to say opposite displacements, then I noticed that to be opposite, they should have the same magnitude and opposite signs. But here, no. This pulse is larger than this pulse. So we can't say that they are opposite. They have opposite orientations. The interference or superposition in this situation is referred to as destructive or DI. So two types of superpositions, constructive and destructive. That's it concerning this part. We just introduced the difference between constructive and destructive interference, and we also talked about the meaning of interference or superposition in the first place. All our study was in one dimension. Later on in upcoming sessions, we're going to talk about interference in two dimensions. Now, I want you to solve these two applications. Okay, take them as homework, solve them alone, and don't forget that at the end of each lesson, after having some sessions about explanations, we're going to have one session which is dedicated to solving these exercises. Solve these for the time being. Then, after you finish watching all the other videos, go to the solution video and check your work. Okay? Okay, now To end our session, we'll go back to when we talked about the mufflers and the anti-noise cancellation technique. We said back then that the device sends a sound wave which is opposite to the noise, thus cancelling it. Right now, we can describe this with more scientific terms such as we can say the ANC produces a sound wave that interferes with the noise destructively, and we can also understand what's happening. In fact, the noise is a wave that is propagating in a certain way. You can see it here. The device, the machine which cancels that noise, sends a wave which is opposite to it, so that as they overlap, crest and trough cancel out with each other, so the resulting sound is gonna be reduced noise or nothing. That's it concerning this part. Thank you for your time. In the upcoming sessions, we're gonna study more about interference and interference in 2 dimensions. Review what we've said, try to solve the homework, and we'll meet in the upcoming session.